Okay, so here we're doing the domain of a rational function. Basically, that's going to include all real numbers except those that cause the denominator to equal 0. Okay, so we've done things like that in the past. So all we're going to do is we're going to look at this one. So find the domain of this. Well, where is the denominator equal to 0? Well, it's where x minus 1 is equal to 0 and x minus 5 equals 0. So those are the two places where it's going to equal 0. So x equals 1 and x equals 5. So those are the two places that cause the denominator to equal 0. So our domain is going to be all real numbers except x equals 1 and x equals 5. Okay. Now, what does that tell us with those two? Well, those are going to be vertical asymptotes. So those will be vertical asymptotes at x equals 1 and x equals 5. So that's going to help us when we have to start drawing graphs just based on an equation without using our calculator. So that'll be something that's going to eventually help us here. Okay, so we got those vertical asymptotes. All right. So if we're given a rational function, we can identify any vertical asymptotes of the graph. So we factor the numerator and denominator. We note restrictions on the domain of the function like we just did. Then we reduce the function by canceling like terms in numerator and denominator. So if for some reason, we factored this and x minus 1 was in both of them, we could cancel those out, okay? Note that any values that cause the denominator to be 0 after canceling are where the vertical asymptotes occur. And any restrictions in a domain where asymptotes do not occur are called removable discontinuities or holes in the graph. So those removable discontinuities occur in a graph of a rational function at x equals a if a is a 0 for a factor in both the numerator and denominator. So that's when we cancel in the numerator and denominator. If it's in both of them, it cancels, and so that's called a removable discontinuity. Now, if multiplicity is more in the denominator, then there's going to still be an asymptote in that value. So if we had like x plus 1, x minus 1 over x plus 1, x plus 1, x minus 5 or something like that, that would be a removable discontinuity. But because we have multiplicity greater than 1 in the denominator, it's still going to be a vertical asymptote. Now, if this had been, say, a 4 instead, then we just have the removable discontinuity, and then we wouldn't have a vertical asymptote if that was a 4. But if that was a 1, then we would still have it there. So it kind of depends on what we have in that denominator and what we can and cannot cancel out completely. Okay. So what we want to do is we want to find the vertical asymptotes and the removable discontinuities for this graph, all right? So what do we have to do? Well, we have to factor, all right? So the numerator, well, that's the difference of squares. So that's going to be x plus 5, x minus 5. So that was the easy one. Now here we can factor out an x, it looks like, and then that leaves us x squared minus 6x plus 5. Now with this plus 5 and this 6, I'm betting it's going to be x minus 1, x minus 5, because I have to have a negative times negative to get a positive, and two of those add together give us the 6, so 5 and 1 is 6. So if we square that out, it's x squared minus 1x minus 5x minus 6x plus 5. So now that gives us all over x times x minus 1 times x minus 5, okay? So what do we have now? Well, let's go ahead and see if we can cancel anything. Well, x minus 5 cancels. All right, so that's that. Now we want to find vertical asymptotes, removable discontinuities of the graph. Well, first, what is our domain? Well, a domain is going to be all real numbers except what? Well, we can't have 0, we can't have 1, and we can't have 5, except x equals 0, x equals 1, and x equals 5. Now, those are all nice because when you take them over, they become positive. If you would add x plus 1 here, then that would be a negative 1. But we all know how to set those equal to 0 and then solve for x, so that's not a problem. Now, vertical asymptotes, that's what we are left with after we cancel. So we cancel, we have those. So our vertical asymptotes those are going to be at x equals 0 and x equals 1. And then what we were able to cancel out, that's a removable discontinuity. So that would be that. Okay, so first we had to kind of find our domain, and then after that we could get a vertical asymptotes and a removable discontinuity, and that was after we factored. We could just start canceling, and so that would, all of them are going to be the what we say except for what's left after canceling, that's going to be the vertical, and what was canceled, that's the removable discontinuity. Okay, all right, so a lot of stuff on this slide, but it all kind of ties in with what we were looking at there, but it kind of comes into a different play here. So horizontal asymptotes. So those describe the behavior of a graph as input gets very large or small. Okay, now three possible outcomes. Now, if the degree of the denominator is greater than the degree of the numerator, we get a horizontal asymptote at y equals 0. Okay, so that's just given as long as we have this greater than part here. Okay, so if we have that greater than part, then that's going to be our y equals 0. Now, if the degree of the denominator is less than the degree of the numerator by 1, we get a slant slope. Now, the equation of that line is found by long division, where the quotient is the equation of the line. So, if we do something simple, say like x cubed over x squared, that's 1 less. And so x squared goes into x cubed, and we just get x. And so our equation would then be y equals x. But, if you have other items in here besides just the x squared and x cubed, then you're going to have a little bit more work to do that long division. This was just something simple, so I could show you that in this case, then it would be something like, y equals x. Okay. Now, if the degree of the denominator equals the degree of the numerator, we get a horizontal asymptote at y equals a sub n over b sub n. And so that case, maybe we have a 4x cubed plus 3x squared minus 4x. And up here we have maybe a 3x cubed plus 4x minus 2. And that's what our two polynomials are. And so what this says, if those degrees are the same, x cubed, then we just take our leading coefficients, which is in this case 4/3. And so y equals 4/3 will be our horizontal asymptote. Okay, so here an and bn are the leading coefficients, so those two terms there of the p and the q for p over q of x, basically. And again, q of x cannot equal 0, just like we saw before. But those are just going to be our leading terms, and so that's what we took. We took that 4/3, and that was our a over n. Now note, a graph of a rational function is never going to cross a vertical asymptote. Okay, so if we have a vertical asymptote, you're not going to have it going across that. But it may or may not cross a horizontal or slant asymptote. So sometimes it can go across those others. Okay. Now, rational functions may have many vertical asymptotes, but at most one horizontal or slant asymptote. So that's kind of a key there. So you can have many vertical, but at most one horizontal or slant. Okay. Now, the end behavior again is going to mimic the behavior of the reduced end behavior fraction when degree of numerator is greater than the degree of the denominator by more than 1. Okay, so if we look at this one, we have a 5x to the fifth over the x here, and so we're just looking at that beginning piece here. So it's going to have the end behavior of 5x to the fifth over x, which if we reduce that is 5x to the fourth. So it's going to have the end behavior of 5x to the fourth. Okay, so that's going to help us kind of reduce and figure out that end behavior by reducing just that beginning terms of the thing. Now, if it had been 5x to the fifth over 2x to the third, then our end behavior, well, let's write it 5x to the fifth over 2x to the third, then our end behavior is going to be 5 halves x squared. So it's going to look more like that for our end behavior if we had those as a beginning term here. All right. So intercepts of rational functions. So the y-intercept will occur when the input is 0. So if the function is defined at 0, else it will not have a y-intercept. So basically plug in x equals 0 and solve for y. Now, if we have a vertical asymptote at, x equals 0, then we're not obviously going to have a y-intercept. Now, the x-intercept will occur where inputs cause the output to be 0. So since a fraction is only equal to 0 when the numerator is 0, x-intercepts occur when the numerator of the rational function is equal to 0. So we set the factor numerator equal to 0, use the zero product rule to get values for x. So, we might have a x squared minus 25 over 3x cubed plus 4x squared minus 5x. And to find the x-intercepts, we just take x squared minus 25, set that equal to 0. And so x minus 5, x plus 5 equals 0. So x equals 5 and x equals negative 5. Those are going to be our two x-intercepts, basically. Okay, so that's how we can use our fraction, our rational fraction here, to find our x-intercepts. All right, so let's stop there and we'll come back for more.